All right, so let's talk a little bit more about linear classification, and we'll talk about linear discriminators. So, linear classifiers, as we discussed in Lecture 1, use decision boundaries that are linear. So we would have a straight line for two variables, a plane for three variables, a hyperplane for four or more variables, and so on. And these classifiers produce only a single boundary, so they will separate only two classes at a time. Now, they can be applied to subsets of the data to identify more than two classes. So the class that's predicted by a linear discriminator is given by the output of a linear equation. Y is equal to the sum of x sub I, w sub I, plus b. So if we just had two variables, then this would be basically a straight line. So b is your bias or offset, x sub I is your input variable, w's are the weights. So this can also be thought of as the slope of a line. So if y is greater than 0.5, then the classifier will predict that the input data belong in class 1. If y is less than 0.5, the classifier will predict that the input data belong to class 0. And class 1 and class 0 are just arbitrary names for two classes. So the output of the linear classifier to any set of input variables is determined by the weights, these w sub i's, and the bias b. So the bias b can be included as one of the weights, and this basically simplifies the equation as long as you add an input and let that input be 1. So our sum, rather than going from 1 to n, becomes 1. If we have m variables, goes from 1 to m plus 1, where x of m plus 1 is 1, and we basically have then just the weights. So basically your weight at m plus 1 is going to equal b, your bias or offset. So the weights and the bias are basically the free parameters of this particular classification method. And sometimes linear classifiers are optimal. A linear boundary is certainly the best way to separate two Gaussian distributions. They can be easily implemented and very quickly trained. So a known class is specified by a variable d, where d is 0 or minus 1 or 1, representing class 0 and class 1. In a case where you have more than two classes, a lot of times d will be given as a digital variable. So you can see that d here is basically a set of 1s and 0s. And the reason that you would do this is it just makes the programming easier, since we basically are representing a class as a bit stream. Okay, so how do we actually do our training? The way that the training is done is it's using the least squares algorithm. In other words, we're taking the sum of squares error between the output of the linear classifier and the correct class. So our correct class minus our output of our classifier squared, and then that gives us the square error. So the sum of square error, so then we sum it up and we get the sum of square error. Now what we want is we want that to be minimized. And so what you want to do when you, and we can write that, by the way, in matrix notation as the following. So what you want to do is, because let me just go to this step real quick. The reason you want to do this is, if you look, this is this matrix multiplied by itself transposed. What that does is that basically gives you this sum. So remember, matrix multiplication gives you a sum of rows and columns. So by doing the transpose matrix times itself, we're giving you this sum. So in order to minimize the sum square error, you basically differentiate it with respect to w, the weights. Set it equal to 0 and solve for w. So what we're doing there is really taking the derivative, and then we're setting the derivative equal to 0 in order to find a local minimum. If that's non-singular, we can come up with a unique solution that's given by the following. So your unique solution for w is X transpose X inverted, and then X transpose times D, where D, remember, is your correct classification, and X are your input variables. So just an example, we can generate a test set consisting of two Gaussian distributions that have centers of 3 standard deviations apart. The test set will include the correct classification vector D. We're going to apply the least squares method to classify these two data sets and then plot the results. The two classes will be plotted as circles and squares, and we'll plot any misclassified data points filled in black. And finally, we'll plot the decision boundary that's produced by the linear classifier. So there is a routine generate data that's given by your author in the associated chapter files. And so it contains the syntax mentioned here. And so I'll skip over a lot of this. Here is the MATLAB algorithm, and then for plotting the results, basically, and evaluating the results of a linear classifier, plotting the linear decision boundary. Okay, so here is the result. So here you can see boundary. Here you can see some other boundaries that also appear to separate the data set. And so, in fact, there's an infinite number of boundaries that could be used. So the question is, what's the way to determine the best boundary? The best boundary is basically to train on the least squares classifier. So let's look and see. So here's what happens when we now show some classification errors that will occur if we train our classifier on a smaller data set as compared to if we train our classifier on a larger data set. So here we have 12 classification errors when we have n equals 20. We only have 2 classification errors when we have n equals 200. So important that the training set is as large as you can possibly make it in order to avoid problems with generalization. So this matrix is referred to as the confusion matrix. So what you have is you have your actual class, and then you have your predicted class. And this is an example where we would have 3 classes, class 0, class 1, and class 2. So if your predicted class is class 0 and your true class is class 0, then that's your percent correct. So like if you had 20 people and 10 of them were known to be class 0, but only 9 of them were predicted to be class 0, then you would have 90% correct. Let's say that one additional person was considered to be a part of class 1, predicted to be a part of class 1, but they were actually class 0, then you would have a 10% error. If no one was predicted to be class 2 who was actually class 0, you'd have a 0% error. So for every class, you have a percent that are correctly predicted and classified, and then you have a percent that are incorrectly predicted or classified. So there are 2 key measures for a 2-class classification scheme: sensitivity and specificity. So a true positive would mean that you predict something will be in a certain class, and it is in fact in that class. A false negative would be that you would predict something would not be in a class when in fact it is. So this would be the person who should have been in category 1 and was actually predicted to be in category 2. So that's referred to as your sensitivity, and it's the percent correct detections. So in our previous example of 9 and 1, that would be 9 true positives over 9 true positives plus 1 false negative. So that would be a 90% sensitivity. Specificity means what is the percent correct rejections. So in our case, we would have 10 true negatives and one false positive. So we would have 10 true negatives, so we would have 10 over 11. That would be our specificity. So the receiver operation curve, or ROC curve, plots sensitivity versus specificity. And sometimes you can vary the decision boundary to increase or decrease the detection of abnormals. If you increase the detection of true positives, that will usually increase the number of false positives and will lower the number of true negatives. So there is a trade-off between sensitivity and specificity. So let's look at what this curve looks like. So if you're on this center line here, you basically are just looking at chance. And note here that specificity is plotted in the reverse scale. Sensitivity plotted from 0 to 100, specificity plotted from 100 to 0. So obviously if you have 0 sensitivity, you have 100 specificity. And so this is basically a curve of chance. As your performance improves, this curve approaches the axes. And at this point, where you're at 100, 100, you basically would have perfect separation. So a particular decision boundary might put you somewhere along this curve. Okay, and at this point, we're not going to go through the MATLAB for this particular example, but let's look at the interesting result. So here's a mixed group where the circles are diseased and the squares are normal. And you can see in the middle here, there's a great deal of overlap between the two groups. This is very common in biomedical problems. You just have some that are not clearly separated. Now, maybe this means you didn't make a good choice of features. So maybe you picked the wrong X1 and X2. For example, if you have 60 channels of EEG data, maybe you picked the wrong 2 channels. And so there's a whole portion of pattern recognition associated with the correct selection of features. So how do you figure out what would be the best X1 and X2 you could use? Once you figured out the best X1 and X2, and I will say a lot of times you do try to do a preliminary, you either try to do maybe a preliminary data reduction through principal component analysis, or maybe you will do a preliminary statistical analysis and see if you come up with statistically significant differences between different variables for different groups, and you sort of use that as a way to threshold off what variables you do and do not look at. Sometimes you only have 2 variables, so that's your only choice. So, but you can see here in this data set we have quite a bit of overlap. Now what's happening here is our linear separation, and basically we're moving the threshold. So that would be that B number. So B is being varied, and you can see that, okay, in this case, you don't have any misclassified normals, but you have a lot of people with disease who are not accurately classified as having disease. So you will have a lot of false negatives. As this curve moves, now you see that you're getting some people who are not diseased who are classified as diseased. And you've picked up a few more true positives in your diseased group. These 2 blue circles here are now showing to be diseased. These 2 points here showing to be diseased. And so as you move this threshold, you are adjusting the sensitivity specificity trade-off if you're defining that with regard to diagnosing the disease. So a blue circle that is correctly classified, a circle that is correctly classified would be a true positive. So anyway, this just illustrates how there is a trade-off here, and why would you make a particular decision in a particular way? Well, perhaps if you're looking to use this decision to determine whether or not to make more testing, but maybe it's expensive testing, so maybe you've used some kind of preliminary imaging and you're doing a sort based on that preliminary imaging, and then based on what the results of that, you'll do a more expensive MRI or PET scan. In that case, you might want this kind of thresholding, because you're basically just, you want to be sure that everyone with the disease is correctly identified as having the disease. And the people who don't have the disease, okay, it's cost you a little more money to run an extra test, but that's probably okay. In the case where maybe you're going to do an invasive surgery or a risky procedure or use a high-risk drug, say you're diagnosing heart disease based on high cholesterol and hypertension levels, and you're trying to make a decision whether or not to use a statin drug, then maybe some of these people who are kind of in the middle and not a clear diagnosis that they have heart disease and need to be treated, if the drug is high risk, maybe you're okay with some false negatives. So anyway, it kind of depends on the situation that you're looking at, where you want your threshold, and how you want to do your separation. So here's an example of the data set that was modeled earlier. These were two closely spaced Gaussian distributions, and the classifier was a linear least squared. So here's what the curve, the sensitivity specificity curve looks like, and here's the selected B value on that curve. So basically, this is plotting those threshold values, and this is the selected choice of threshold value. Now it is possible to do higher dimensions separation, in other words, nonlinear separation. The classic way to do that is to use a kernel machine. What the kernel does is the kernel basically transforms your data into a higher dimensional space. And Cover's theorem tells us that if the number of dimensions is high enough, you can always find a linear boundary or a hyperplane that will separate the data without any error. So rather than using a nonlinear separator, you're going to take your data themselves and do a transformation to a higher dimensional space so that a linear separator will work. So here's an example of a two-class data set. You can see that clearly they would be separable if we did some kind of figure-8 space. But rather than define a complicated boundary, let's see if we can use this function where x1 and x2 are our two variables. See if we can use this function to physically move and transform the data set. So let's come here. So here is a three-dimensional feature space because we've now added that cross term. And you can see that the data physically move in such a way that if we now put this plane in here, we've completely effectively separated the data set. So this plane separates our data set. And so we've been able to do it with a linear separation instead of some kind of complicated curved space. This can avoid overfitting of the data. The problem is your data are no longer, the dimensions of your data no longer represent the true original dimensions. So you have these extra, so if you were trying to relate this to something physical, like let's say separation of heartbeats compared to maybe difference in magnitude of a P wave and a Q wave in an EKG. So if those were your two features, and you've now done this data transformation, it's more difficult to do a physical model of how the individual features contribute because you've basically done a nonlinear data transformation. And as you know, most nonlinear data transformations are not reversible. So it's not like a Fourier transform, which is linear. It's a nonlinear transformation.